Okay, hi. So my name is Joyce, and I'm here to present this thing I've been working on called the Verifiable Computing Project. So the question that we ask here is, how do we build trusted open hardware, right? Wait a minute, what's going on? So yes, this is what we're going to be covering in this presentation. Why do we care about verifiable computing? Why use FPGAs, and all of that, right? Which we'll cover in this talk. What we will not cover is basically things like computer architecture, digital design, or VLSI design. So there's that. So, what do all of these devices have in common? A server, iPhone, and PLCs. They're all computers, right? So if you're an end user, as an end user, you're going to ask a question, how do I know that the devices I use are trustworthy? And for a chip designer, you may ask a question, how do I know that if I send a chip to the fab, that the chips I get back are exactly as per the design and they are not tampered with? So here's a real life example, right? So there's this case I've worked on where there was an iPhone 10 that got compromised. What's that? The adversary was able to hear, and know what was going on a Zoom call that was happening live, and they could message us live, right? What we were saying on the Zoom call. And when the phone was taken by the police and it did forensics, they could not find the entry point. They could not find any traces of spyware, stalkerware, and any sort of stuff. Huh? Sorry? We don't know. Until now, they were not able to find anything. That's the thing. And the phone was not jailbroken by the owner. So and the kind of point I'm trying to say also is that like these devices might as well be they are black boxes to their owners, right? So here's another example. Here's a simple CMOS inverter, right? Try spotting the difference here. Not easy. So it's not so easy, right? So if you look carefully, you can tell that the doping type has already, as if you compare here and here, the doping type hasn't changed from a P type to N type. So yes, no matter what you put through this inverter, it always give you the same result. That's and there was a paper published around, I believe, in 2013 that showed that you could do dopant level attacks, on a chip, and specifically it was an Intel Ivy Bridge, a random number generator, right? So. So yeah, in that section when they modified so-called the rate matcher, so you got two registers. You have the register K and got the register C, which then in the counter mode increments by 1, right? But what they can do is that they can actually tamper with the registers in a similar way, so yeah, they can basically make the RNG not so random anymore. And this is where they actually did the. This is not the whole RNG, right? This is just one section of it where they did where they did the tampering itself. And effectively what they could do is that they can by this modification they can basically how do I say, like, they can actually create a number that looks random, but they actually control the actual number of bits of entropy, right? And yes, what they also were able to show in this paper is that they can also cheat Intel's built-in self-test. And yeah. So I mentioned all of that, with the Ivy Bridge random number generator. But I do want to give a caveat because when this paper was published, apparently there was a method that there was already a method that could detect like doping, right? The kinds of doping on the chip. And that's more on, like, that's used for things like failure analysis, which the authors may or may not have actually known about at the time. So Andrew Zonenberg and John McMaster, they took a sample of a chip, they stained it, and they were able to show that, hey, by the color, just by looking at what is that? Which areas are darker, which areas are lighter. They can actually show that, oh, which parts are actually P-type or N-type. So that's the caveat I do want to give, because I gave this presentation before back in 2022, and I did not know of it at the time, but now I spoke to people like Andrew, and he said yes, this is a method that can be used to detect this kind of Trojan. Well, I think the point is this sort of attack it is easier for a state level actor to carry out, right? But it's costly and difficult for companies, or chip designers to inspect the fab process, and it's very difficult to know that a chip, to detect tampering unless you already suspect there's tampering, right? So if you're dealing with a state level actor, and maybe you have someone that is that's already pliable working at the fab, you're not, like, this sort of tampering is not so likely to be noticed. So this is the assumptions that we are making, when we think about these kinds of attacks. So the current state of things, when I talk about like open hardware, and that kind of process, is that yes, you already have open source process design kits. You have programs such as Tiny Tape Out, where you can actually design your own, simple chips and then get it back in a few months. So these PDKs do already exist, but an open source chip fabrication process doesn't yet exist. Although there have been hackers around the world, like in the US, and I know that there's some groups here in Europe as well who are actually working on building their own experimental chips, their experimental processors, or that sort of thing. So barring an open source chip fabrication process, what can we do for now, right? So in this in this example, we're going to use FPGA, right? And why use FPGAs? Because they are general purpose devices, and they are used in so many different devices and applications that it's difficult for any attacker to design specific attacks in silicon. And it also allows a user to, if you have the hardware description language code, you can inspect that code, and you can verify that the device correctly operates based on that HDL, and you can customize your device if you desire. And this is the general structure of FPGA, right? So you have the configurable logic blocks itself. You have the switch matrix that connects, all of it, and then you have the I/O blocks. And in let's say, the lattice ICE40 FPGA, which is what badges like the MCH 2022 uses. So this is how it looks like. You have the programmable logic blocks, and all of that. And inside the programmable logic blocks, you have a lookup table. You can carry logic, so on, right? And well, you can actually set, okay, this is I/O bank and I/O cell. You can set, whether this pad is input, output, all that sort of stuff. And there are already existing works that make use of things like this, like Bunny Studio's precursor. So Bunny already gives you like the whole design, right? Like you can see that this is the untrusted domain, the U domain, which handles things like power management, things like that. And this is where your and this is where your trusted domain is. This is the FPGA here. And the idea of the precursor is that you can use it as a secret store, right? You can use it as a secure wireless messenger, secret store. You can store all your keys inside the FPGA. And you can do, and the way it works is that if you need be, there's a kill switch that you can just activate, and it will destroy all the secrets that's stored in the FPGA itself. And yes, it gives you the on this like the gateway level. He already gives you how the thing is designed, like all the buses and all that. And this is how the whole thing looks like inside the FPGA. So in order to talk about FPGAs, we need to talk about the design flow of FPGAs. So what you have is that you start out by come up with your description, like what do you want to build and things like that. Then you write your HDL, you synthesize the design, and then after the synthesis, you do things like place and routes. So the synthesis describes the logical connections between the blocks, right? The place and route takes that design, converts it to a physical implementation based on which FPGA you use. And finally, you get to the process of bitstream generation. You generate the bitstream file for the specific CLBs on the device. So there are already, a few tools for that, like USYS and XPNR, and there are, for bitstream generation, there are multiple projects under the FPGA project. And it aims to be the GCC for FPGAs, right? So they already support things like the Xilinx 7 series, Lattice ICE40, ECP5, that sort of deal. So yeah, so on the front end, USYS does the synthesis, and then you have on the back end you have things like NextPNR that does the place and route. You have the different projects like IceStorm, X-Ray, and all that contains the specific definitions for whichever FPGA you're looking to use, and and then tools for like Verilator for verification, simulation, all that. So yeah, this is the current state as a few days ago of like what have they documented, for the different projects. For now, the Xilinx 7 series under Project X-Ray, there's still work that needs to be done. It's still not complete yet. So another tool chain I want to talk about is LightX, which I'll show a demonstration later. So the framework for building system on chips with FPGAs, and you can take a RISC-V, whatever core, you can combine it with whichever IP you want, and you can generate, your effectively your own SoC, and it uses MyGen FHDL, which is a Python-based HDL. So yeah, and yeah, this is the current state of this is the state of things as at 2018. What IPs it supports, what soft cores, and what boards. Well, of course, right now, it supports a lot more FPGAs, a lot more platforms, that sort of thing. Yeah. So the design that we're gonna use today uses this thing called the Acon CLE 215. So it's it's an RTX 7 FPGA, and it's a repurposed crypto miner that's now used as an FPGA development board thing. So if you open the file under LightX, you can see that this is the board definition. You can see that, here's the LEDs, which pins is using, where's the SPI flash, PCIe, and so on. And we are going to use RISC-V for this demonstration. Why RISC-V? Because it's open source, and if you're going to implement like a 32-bit, RISC-V 32i processor, that's less than 50 instructions. The base instructions and standard instructions have already been frozen, so you don't have to worry, things are going to change and things like that. And you can also make your own custom extensions if you wanted. And yeah, this is how few instructions, in RV32i. So yes, as I said, we're going to use the CLE 215 repurposed crypto miner thing, for this. And this is what it has. As I said, RTX 7 FPGA, a bunch of flash, DDR3 memory, LEDs, that sort of stuff. And this specific FPGA is basically the highest end FPGA in the RTX 7 family. Well, so right now, so we're sitting in Singapore in one of my friends' bedrooms. This is the setup, as it is right now. It's going to be finicky. I've had the VM crash on me a few times. So yeah, let's do the demo. Let's see. Okay, so what I'm just going to do is I'm going to attach the JTAG, and I'm going to attach the serial. USB 1, that should. So yeah, so once you flash the once you flash the bit stream and FPGA, this is effectively what you see. it gives you the light X BIOS, does the SDR initialization and all of that. So if so, I had a setup that actually supports things like SD card or SATA or whatever, you could install Linux, onto a SD card or whichever drive, well, that's pretty much it for the demo, you know. Let's see. So yeah, there are some ongoing projects that I'm working on right now, such as the Forerunner laptop. We are building a laptop, with the same principle. So you use FPGA on a CM4 form factor, so you can build you can build hardware that's general purpose, and also that you can verify, and you can see how that hardware works and things like that. Another project is the Airwave project, which is in a similar vein, but we're looking into things like mobile security. How can you be sure that your baseband firmware, the baseband processor, is actually clean, that sort of stuff. Yeah, so we are looking to use eventually post-market OS for the Airwave project. So yes, final thoughts. There are two questions that any such project will have to ask. As a user, what tests can I perform so that I can trust the hardware I use? And the second question, how can I trust the tests? Because especially if you're a layperson, right? If you tell a layperson, hey, do these tests, you get these results. Then the question you're gonna ask is, what do those tests mean? How can I trust those tests? And I don't think that any direct or easy answers, and I think that any practical solution to the questions that I've asked must necessarily involve, a mix of tech and social considerations. We need to, whatever way we find, we need to engage with non-technical users so that they can better understand the tech that they use, they can better understand security and the implications, of certain things. And yeah, that's pretty much it. So yeah, here's the papers have been.
The slides are available online?
I need to upload it.
Okay.
Yeah. But yeah, questions?
I have to finish this first. You should certainly talk to Frans, because he had a similar college on software bootstrapping. It's very interesting, this talk, because I have questioned this myself, when you doing stuff which is quite confidential, and all kinds of institutions, including the government, ask you to use some iPad, some Android to do that. This is a very good college, because I have been wondering about this stuff as well. When you have complicated devices like mobile phones, etc., to do extremely confidential stuff, and you don't know whether the phone has not been tampered with. And that's a very this is a very interesting topic. And now I forgot my question. That's why I prefer, for example, for banking, you can have a banking app which runs on some hardware. And I trust simple devices like challenge response devices, which are simpler to use, to do exactly the thing that they should do. It's very specific functionality. And this is interesting because fortunately in a hacker conference there was a badge which contained an FPGA, so I could understand a little bit. I'm a totally FPGA beginner, and I would like to thank you for this. Thank you.
Thanks for coming.